Right, so the second talk today is actually the first in a series of two, so the continuation will be on Friday, and it's Victor Chulaevsky, and he will talk about multidimensional deterministic disorder and understand localization.
Thank you very much. In the previous talk, Peter regretted the lack of periodicity and ergodicity, right? I think I could make up for him because there will be some almost periodicity and some ergodicity, but we shall also see that neither is crucial for at least part of the results, which I am results and methods I'm going to present. Well, it's obviously about localization in deterministic systems, but the key word here is actually this. Multidimensional, because indeed we heard in this program alone a number of talks about one-dimensional quantum systems, and basically the operators we are going to discuss are of very simple form. It will be discrete Schrödinger operator on some lattice, and the trick is how to take its potential. Well, the potential in this series of talks will be deterministic, meaning that it is generated by sampling some function on some probability space, which is a phase space for a dynamical system, okay, with a multidimensional time, abelian multidimensional time ZD, and from the very beginning on the work on this project, I tried to put as much distance between myself and the specifically one-dimensional techniques. So it was intentionally made so that the results would be extended or naturally appear in the multidimensional context. So usually, the basic result, or I mean, basic example, basic class of examples, many people here or in virtual audience may be interested in, is given by the quasi-periodic potentials. In this case, we have to have as omega a torus, and this is a basic example. The dynamical system will be given by minimal rotation, or sequence of familiar rotations of the torus, and that's a rich class of examples. But you will see, as I already mentioned, that quasi-periodicity and even more generally almost periodicity is not essential for at least a large part of the results. Now, usually we take just one sample function and ask all these questions. What about spectrum? What about eigenfunctions, and so on and so forth? Local statistics, for example. But there are many questions which cannot be answered, at least not easily, in full generality when we allow the dimension of the configuration space for the Hamiltonian, and also dimension of the phase space of the dynamical system. Well, as soon as we start to speak about dimension, we need some nice geometrical structure. So let's, for the purposes of this talk, treat only the dynamical systems on, let's say, torus. Or more generally, it could be Riemann manifold, but at least for the dimension, we need something. Well, so let's stay with this class of examples.
So reality is ergodic, right?
It may be ergodic. It's a good question, but I will remind with it.
Victor, there is a stupid question. What is t in power x if x belongs to Gd? I understand t quadrat, t square, t cube.
T to the power, which is a vector of dimension d, is t1 x1, t d x d, where ti is commute. It's an action of the
Does this
group.
mean that your T there in the second line
Yeah.
is kind of a whole family of operators?
No, but just imagine T on the second line, and instead of writing T open parentheses X comma W, right? You just, sorry, he put in the second omega comma X. You write T to the X applied to omega. It's just another way of writing a function applied to two operands. Instead of putting them on a line separated by parentheses, you call it X omega. It's just another way of writing things, that's all.
Yeah, I know that it's always just another
Shift,
way of
so
writing.
that's fine.
Horizontally or vertically gives you two rotations of the torus. So when you
Yeah, but what does it mean then if you have here T1, TD?
Right.
So the T which you write in the second line, it is always T, it's also meant something like a
no,
whole set of
T without superscript or subscript, it's just an application. It's an action of the group ZD on omega, preserving the measure. Just an action by isomorphism. Okay, so we know that for analytic Hall functions or sampling functions V, in this for example on the say on the torus, there is a deep theory going back to the beginning of this millennium. Gauguin, Bernstein, Schlag. Sylvius Klein showed that a part of this result survives going down to Gevrey class. But how about finite smoothness? Can one prove unknown localization for some class of non-analytic or not even Gevrey, let's say C3, C2 functions? And how generic is like Anderson localization, if ever it takes place? Well, I can ask a more dire question. How about continuous but no differential halves? Is it completely crazy to think about crossings, divergent geometry of intersections, transversality in a situation where there is nothing to do for a geometer? Well. Speaking of local statistics in double or probably triple quotes, can one hope for some as weak as possible analog of the Wegner-Minami hierarchy for the deterministic potentials? And, for example, if these estimates are not nearly optimal, can one at least make some good use of them and to prove a simple spectrum, or assume that we already proved that the spectrum or part of it is a pure point? Well, nearly 20 years ago, the Rio, Zhytomyrsky, Last and Simon put in a title of a subsection in their paper that uniform localization of eigenfunctions fails in many models, and there are deep topological reasons for that when it fails. Still, there are some examples, but the examples we know are there. First, either refer to analytic situation like the Maryland model, or its generalization by Belisar, Lima, and Coppola in '93. By the way, that paper predates multiscale analysis and uses Kolmogorov-Moser method. There are also examples where uniform localization of eigenfunctions occurs for limit periodic potentials. It's it's a couple of works by Damanik and Gunn, published in 11 and 13, if my memory serves. So how about a richer class of examples, and, for example, for not almost periodic potentials? Well, slowly the n-particle or many-particle, multi-particle, few-particle localization theory moves forward, and can be asked about other localization, for some examples, for more than one particle. Let's say in quasi-periodic media. Well, and like I said in the very beginning, can we abandon almost periodicity, let alone quasi-periodicity? Well, there are many questions, and fortunately, one can give at least some answers to these questions. However, there is a price to pay for that. Well, one has to change the general approach and abandon, from at least in this context, abandon the idea of treating one individual sampling function or half, as they are usually called in the context of almost periodic functions. So if you give me one nicest function, the loveliest which you can find, and ask me something about this function alone, most likely I will have no answer at all. But like in the random operators, well, you probably heard the story told about Pastor giving the talk in 70s, early 80s in St. Petersburg, where he was asked by analysts, well, it's very nice, but can you give one particular example of random operator having a pure point spectrum? Here the situation is somewhat similar, but there are differences, because as far as the disorder, as we usually understand it, is concerned, the disorder, without cause, is determined by the nature of the dynamical system. And if the dynamical system is, say, rotation of a torus, then it will be always quasi-periodic potential. However, the choice of the function, of the sampling function of the torus, it is what we allow ourselves now, and it so happens that we can show that many typical choices are good for localization. Okay. Now, yeah, so the kind of results one can hope for and one can prove are of the following form. We have to first introduce in the Hall function an additional parameter, and one it is convenient to consider this parameter, the point small theta, as the element of another additional auxiliary probability space. Well, any measure space would be good. You only have to know how to define this new measure of the parameters. But if the measure is finite, which is quite natural to assume, if you construct, you can fight for it. And if the measure is finite, why not normalize it? That's why I'm using a language of probability space, even for the parameter space. Okay, so the kind of result we can hope is that in the whole parameter space, there is a generic subset, capital theta tilde, such that for any theta in this generic subset, we have, for at least for the disorder amplitude large enough, one or another property. So the crucial point here is that it really so happens that to prove for something for almost every element of theta, you have somehow to take larger and larger amplitude of the disorder depending upon the choice of the parameter.
The functions phi n stay fixed.
Yes, they are fixed. Yeah, they are fixed from the very beginning. And all the parameter of freedom is only in the expansion coefficients. Of course, it's just one possible way to introduce this parametric freedom. It happens to be fruitful. Okay. Yeah. Well, so there are two different kind of disorder in this model. Well, the spatial disorder without quotes and disorder in quotes, which is actually a parametric freedom coming from this expansion of the Hall function over a series of a sequence of functions. By the way, I never said, I will never assume that these functions, small functions phi sub n, are orthogonal or bi-orthogonal. No, it is not required. At least there are good examples where there's no shadow of orthogonality, but the functions are good enough to produce enough freedom in the hull function. Okay. Okay. So yeah. Now, what kind of negative effects we are going to eliminate, circumvent by using this additional parameter? Well, first of all, localization, or let's say proof of localization, is about resonance and how to rule them out or avoid, or let's say show that they don't accumulate, so that the quantum particle cannot really propagate, make an infinite sequence of jumps to the infinity, so that the state is not an L2 but generalized eigenfunction. Usually it's about resonances. And resonances, if we look in the very simple example of almost periodic operator. So let's say we have a finite interval in one dimension. And let's speak for the moment not about the operator in the whole lattice, but just on the finite interval. Each value of the potential without any theta is v, the Hall function of omega plus x alpha, where alpha is the frequency. Then if we take the operator h without the Laplacian, we get just the diagonal operator. This is a finite dimensional matrix. On the diagonal, we have the entries v of x, and if all v's are just distinct, pairwise distinct, then we can always make so by taking as a large coupling constant g in front of v. So all the differences are huge. Then if we add this Jacobi strip around it, it will still be our operator, which can be diagonal. Inverse will be diagonalizable with huge distances between all the pairs of eigenvalues. So the crucial thing here is to have all these different. But if we look at the graph of just one v, one x, for the cosine example, it will be the cosine. What are the ranges? Coincidences of the values of v. And of course, we can have the same value of v for two different phases, omega. Yeah. So such situations should be ruled out somehow, either deterministically or at least by probability, by excluding a subset of phases of zero measure. That's what is a localization proof about. And one more point. If you look at the graph of another value of the potential, it will be a shifted cosine. So the resonance between the eigenvalues will become now the interceptions. Okay, so in this context, in the context of the cosine-like potential, not just almost nothing, but cosine-like for a function with two critical points, both non-degenerate and C2. The analysis has been done well, in two independent works by Sinai and by Fröhlich, Spencer, and Wittler. And it was shown that the double resonances, the crossings which are dangerous for localization, may occur, they should occur by topological reasons. However, in the course of the proof of localization, the triple or quadruple, all the resonances of higher multiplicity, higher than 2, can be ruled out. It doesn't mean it never happens for the graphs. It doesn't. It means that when it happens, it doesn't really matter for the localization.
Did they use somehow Bourdain results? Did they, was it before Bourdain?
It was before. It was in the late 80s.
Oh,
Okay. So one might hope to prove the same thing for new dimensional torus, and then by usual very simple arithmetics of the codimensions, new plus one graphs of functions of new variables may have intersections as isolated points, and if you raise even more, go to new plus 2, it becomes unstable. A small perturbation in this space in some functional space removes this multiplicity, which is higher than what is topologically unavoidable. Well, for analytic functions what followed from my discussions from Michigan, it seems that there is no upper bound, no uniform upper bound on the unavoidable resonances in the scheme of proof of Anderson localization. And if in the multi-scale analysis that is used there, the number of possible resonances which you have to take care of grows with the scale. Well, in the context of these ensembles of parametric ensembles of ergodic or non-ergodic dynamical ensembles, which for the lack of a better word I usually call grand ensembles, making a reference to the situation in the statistical mechanics. So it's an ensemble of ensembles. So in this functional parametric context, one can show that typically, if you introduce a good measure in the functional space on the torus, you can prove that the topologically unavoidable multiplicity of resonance is the sharp bound. What is above can be avoided. Okay. And yeah, what is particularly interesting here is that, well, you might think about the usual differential geometrical analysis of intersections, transversality, gradient, hashing, and so on and so forth. But it so happens that by pure measure theoretic estimates, you can rule, you can say that you can avoid, rule out, with good probability, rule out the multiplicity of resonances with a value j, which depends upon the dimension of torus. And in the case if the half function is not Lipschitz continuous, but just Hölder continuous with exponent k, you have to take as a value of j nu over k plus 1. Of course, it should be an integer number, which means that you take what? You take the rounded integer part, rounded below, and you add 2. So for Lipschitz continuous function, you have j equal nu plus 2. This is the multiplicity which can be avoided. Nu plus 1 cannot. If kappa is different from 1, it's really Hölder, not necessarily a differentiable function, then you still have this lower bound. And you can see now that for an entire interval from nu over nu plus 1 to 1, the number of unavoidable resonances is exactly the same as for differentiable functions. It works for any kappa positive, but it works just as for differentiable functions for an entire interval of nowhere differentiable functions.
Sorry, is it, is it easy to see that for kappa smaller than 1, much smaller than 1, we actually need more
of course.
But can we actually see
what do you mean by we actually see that it?
Again, are there obvious examples when you could have many resonances?
No. Everything goes by probabilistic estimates. and therefore no particular example here can be given.
So you cannot really produce
No,
function that is order continuous
absolutely
and
not. Absolutely
such
not.
crosses
No, no.
are unavoidable. No.
At least at this moment, I have absolutely no idea how one can provide such examples, if they exist. Okay, now, yeah. So, to give a hint of what kind of functions phi n are convenient, let's take, like I said in the beginning, the functions phi n needn't be orthogonal. So let's take functions which are just positive, okay, non-negative. In other words, let's take half of each Haar wavelet on the torus. Okay. The Haar wavelet will be a difference of two phis with k and k plus 1. Okay, so these are functions organized in generations. Each generation has a generation amplitude which suppresses their magnitude so that the whole series over the generations converges. First, take care of the convergence. And with the siblings phi n sub k, nth generation, kth sibling, among large capital N sisters and brothers, should cover by their supports, should cover the entire space. I mean, the entire torus. Okay. So then each function of phi and k is modulated by independent parameter. As an analyst, you can just think of independent parameters in multidimensional space. As a probabilist, you can call this random variable in a sequence of identically distributed, for example, identically distributed and jointly independent random variables. So the entire sequence of theta sub nk will be one element theta, making, and of such thetas is made the uppercase theta, the parameter space. Okay, so these theta and k's are better having some good probability density. So you can think about a Gaussian or a uniform, whichever you like. Okay, now how about the correlation structure of the random Hall function on the torus? There will be some correlations, inevitably, which can be seen from the following picture. If we take two points, omega and omega prime, in the torus, omega, okay. Let's say T1 circle, and if both the supports, both points, omega and omega prime, are covered by the same support of one of the functions phi and k, then of course they are correlated. They are correlated through the theta and k, hanging in front of the phi and k. However, if we look at the finer structure and take the phi and k and phi and k prime with disjoint supports, then these functions will be modulated by independent parameters. And therefore, conditional on the initial part of the series, conditional on the initial part of the series for n equals, let's say, from 1 to 10, so that the 11th generation separates omega and omega prime, conditional on the beginning of the series, conditional on some property chosen sigma subalgebra, they have independence of these 2 points, and indeed of any number of points which are separated by the nth partition, by the partition given by the supports of the function phi n with sufficiently large n. And of course, this is good enough because once we have over a sequence of omega 1, omega 2, omega L independent parameters, it's like we have an independent sample. And that's good enough for many probabilistic estimates. And that shows, by the way, why the parameter space is convenient to take it as a probability space or measure space, because it gives rise to quantitative techniques like Webner estimates or Minami estimates. Okay, so this is the strategy. Of course, we have to take care about the possible periodicity and assume some quantitative form of aperiodicity. And in the almost quasi-periodic case, if we assume, for example, Diophantine condition, then we know. So this is now Omega, our torus. These are the points of the trajectory. And we know that 2 points cannot be too close if both x and y are bounded by some given constant, which happens when we take a trajectory corresponding to a affine box for the operator. So what we need is that for a trajectory taken from some kind of cube of size L, we can separate all the points of any trajectory by small balls, and the size of these balls is given by the aperiodicity, uniform aperiodicity bound, which is granted in the case of a periodic, a Diophantine rotation of the torus. Otherwise, such kind of aperiodicity has to be assumed. And by the way, it shows from the very beginning that this strategy can only work for the systems which cannot be hyperbolic, strongly mixing. For example, for hyperbolic automorphism of tori and many other hyperbolic systems, we know that there are lots of periodic points, and returns to the small neighborhood of initial point of a trajectory can be very, very fast. Okay. So this is the first qualitative conclusion, that if we take a rich functional parametric ensemble on the torus, and we assume a periodicity, with some decent periodicity. For example, returns are polynomial or is sub-exponential. Exponential are off limits from the very beginning. Then, in large boxes, where we consider the operator taking the potential by sampling the function small v along the trajectory, we can have some weak form of independence, conditional independence. But of course, taking this conditioning, we may have to raise the conditional probability density, and that will be the price to pay for mimicking randomness and techniques of random operators in the context of deterministic operators. Okay. So again, in this model, where for the moment all the functions phi and k are just step functions with smaller and smaller supports, using this conditional independence, we can have at least conditional Minami estimate of any order. And of course, the factor which will have to hang in front of interval's length may not please you. But at least there is something. Okay. So once this proven for product measure, the measure on torus does not play any essential role in this estimate. The measure on theta does. But once this is proven, you can use Chebyshev inequality and say that the theta ensemble, I mean omega ensembles with a given theta, for which the trace is not as small as it should be, according to this estimated product space, are unlikely by Chebyshev inequality. Meaning that making the choices at random in the functional space so as to produce an ergodic ensemble on the torus, but with sampling from the torus, are usually good. Not as good as for truly random apparatus, but at least qualitatively they're good. For example, you may be sure that typically in the finite volume, these eigenvalues are pairwise distinct. And also, this is all the hierarchy of Wegner-Milami estimate, which comes out of here. And the first element of this hierarchy is a Wegner estimate. And we know in Anderson localization theory that a Wegner estimate may be highly non-optimal and still more than sufficient for the proof of localization.
How does C grow in L?
That depends upon the rate of decay of the generation coefficients. Here, if it decays polynomially, then it grows polynomially. If it grows sub-exponentially with sufficiently small double exponent, it goes sub-exponentially. Okay, and of course, it doesn't suffice for the proof of existence of limiting density of states with the Wegner type estimates, and of course it goes without saying that you can hope for the proof of a local statistic like Poisson statistics. However, it suffices for the proof of simple spectrum. Of course, the first one has to prove that the spectrum is pure point before being able to apply Klein-Molchanov's argument for the proof of simplicity of the pure point spectrum. Okay, now the next natural question is the following. Well, I took as an example the theta n case multiplied by this half wavelets. In this situation, again, by lack of a better word, I use the slang word random wavelets. They are not necessarily orthogonal, but they remind Haar wavelets, and they have random coefficients. Well, how about a more classical example of expansion? Why not take a Fourier series? Well, it makes things harder. Because it is well known that in the numerical analysis that to control the value of a function given by its expansion in a even finite Fourier series over a finite number of infinite trigonometric polynomial, to control its values in a given point through the Fourier coefficients, it's very ungrateful business, because the determinants for the linearized system which arise have nasty habit to be exponentially small. It's a very unstable numerical business. And this is where, again, one has to change the point of view, the general attitude. Forget about the coefficients and look at the random function or random field on the torus they produce. If the coefficients of the expansion are Gaussian, then of course a linear function of a Gaussian sample is Gaussian. You get a Gaussian field. If this Gaussian field satisfies some very natural estimate, a lower estimate for the interpolation error from a neighborhood of epsilon ball of point to the pole, I mean the following. If you know that the Gaussian field is such that taking a point, let's speak about one-dimensional torus, the circle. Take omega and take an epsilon neighborhood of it. Fix the random field outside this interval. Completely. The condition upon it. what will be the variance? But all you need to know a Gaussian variable is the mean and variance. From the very beginning, we can assume that the mean is 0. What about the variance? Well, if the variance here will be polynomial in epsilon, that suffices, by some complication of the argument, that suffices again to prove localization essentially in the same way, which I did not describe yet, as for this toy model with the Haar-like functions phi and k. So the classical expansions are also good, provided, but now let me use proper, and by the way, that's our joint work, which is yet unfinished with Sasha Yosodin, by using and adapting classical results about the interpolation, most developed in the one-dimensional case. I mean, the one-dimensional time. Here it's the time is the torus. But adapting them to multi-dimensional case and to periodic case, one can prove that indeed, if the so-called spectral function of the Gaussian field on the torus decays not too fast, then localization can be proved. Well, in simple terms, what it means not too fast. If a Fourier series converges fast enough, the sum is an analytic function. Analytic function has to have a perfect interpolation property. If you know it outside the ball, you know it inside the ball. So again, from the very beginning, anything like analytic or almost analytic function is off limits. And the Gaussian random field has to have a decent lower bound on the local interpolation property. Okay, this remark was to convince you that not only very artificial functional measures in the spaces of functions on the torus, but quite natural measures, the Gaussian measures on the torus, are good enough to produce you ensembles, parametric ensembles, of ergodic ensembles, of quasi-periodic operators, for which resonances can be avoided. Well, here I just gave a hint how it works. The real work is harder. But using such kind of arguments, one can really prove for natural measures in the functional spaces on the torus to prove Anderson localization, and not only pure point spectrum, but also simplicity of spectrum by a very simple adaptation of Klein-Molchanov argument. Okay, yeah, just to make some example. How far one can go in the decay rate of the spectral function. How fast can decay the coefficients in the Fourier series, so as not to destroy this minimal required for the proof of localization, minimal lower bound on the local interpolation problem. If they decay like that, then the variance in the center of the ball of size epsilon has this form. And you may think that alpha equal to 1/2 is a critical value, because this is where it becomes exponential. Well, actually, even 1/2 is not attainable, at least by the techniques we have with Sasha as of today, because you have to also take into account the dimension of the space and many other things. And basically, we can only work with alpha small enough, depending upon the dimension of the lattice and dimension of the torus. Okay. Okay. Yeah, so it's just a continuation, but when we have the decay of a spectral function of this form, then the probability density which arises in the multi-scale analysis, which is one of the most convenient ways to prove localization in this context, grows like that. And that's not a disaster. not a gift, but not a disaster either. And you can work with it if tau is small enough. Okay, next. So what kind of result, and that will be a natural point to make a stop here. If we assume some decent form of uniform tempered, tempered periodicity, that is a rate of return to a small neighborhood of initial point of the trajectory on the torus, should be bounded from the below by one or another rate. Exponential rate is off limits. Some sub-exponential rates can be treated, but there are many sub-exponential things you might allow. Sub-exponential decay of the coefficients theta n, sub-exponential rate of returns, and many other things, and they start to pile up. So you have to be reasonable. And for example, if you take just a diafunction periodicity, that's good enough. Next, for local interpolation bound. Again, for the interpolation bound, let's assume that given the sample of random field on the torus, outside epsilon ball centered at omega, the variance of the conditional variance in the center has to be lower bound by a power, some finite power of epsilon. If you have both properties polynomial, or power law, it works, and you can prove that indeed there is a subset of parameters, and parameters are infinite sequences of coefficients. Unfortunately, so far, I can't see how one can afford working with a finite dimensional parameter space. I think that would be wonderful, but for the moment, it's out of question. You need an infinite dimensional parameter space. And well, still, all of those remarks, there is a subset of measure 1 in the functional space, in the probability space for this random field on the torus, for which, provided you take large amplitude, which depends upon the choice of the coefficients, the corresponding operator with fixed theta, now we are speaking about ergodic ensemble with respect to omega. This good choice of coefficients gives you an ergodic operator, or quasi-periodic operator, with pure point spectral. And by an adaptation, like I said, of Klein-Martianov argument, you can also prove that the spectrum is not only pure point, but simple. And I don't think there are many examples of where we know that spectrum is simple. In Maryland model, I think it is just tractable by exact solvability of the model, but otherwise seems to be difficult. Yeah. Okay, this is about exponential localization. That is, spectral localization. Eigenfunctions decay exponentially. But in fact, the proof goes through multi-scale analysis, and more precisely through a variable energy or energy interval variant thereof. And it is known since 2001 from the paper by Damanik and Stolman that multi-scale analysis implies strong dynamical localization. Well, you can really apply this argument given by Damanik and Stolman, but again, in 2001, followed another paper by Germain and Klein, who proved exactly that, exactly that implication in a shorter way. So by any of the two approaches, you can prove that not only the H features for a good choice of parameter theta, and for amplitude large enough, depending upon theta, not only it has spectral localization, it features also a strong dynamical localization, which is sub-exponential, meaning that decay of eigenfunction correlators is sub-exponential. The explanation why exponential strong localization cannot be proven in this way is that it goes through multi-scale analysis. I don't say there is no other way, but this is a work in progress. For the moment, the proof going by multi-scale analysis necessarily has to have a decay of eigenfunction correlators slower than exponential, because exponential probabilistic estimates and therefore exponential decay for eigenfunction correlators are off limits for any form of multi-scale analysis that I know of. Okay, and I think the next thing will be about Minami, and let's start with Minami, etc. Next time. Thank you.
Thank you very much. Questions? Okay, so in this case, the continuation will be on Friday 2, I guess, if I'm not mistaken. So let us thank the speaker.